Sergey Kuzin from Harriet-Watt University, and he's going to talk on randomly perturbed dynamic quadratic phase equation.
Small correction that I'm rather from a Ecole Polytechnique, but it is not that important.
Oh, okay.
Okay, so it is my big pleasure to be once again in the Isaac Newton Institute and to give this talk. There is a famous quotation from Henri Poincaré, which was maybe much overused from the community of dynamical systems, that the main problem of celestial mechanics is to study perturbations of integrable systems. So the essence of this saying is that integrable finite-dimensional Hamiltonian systems, we never or almost never find them in a pure form in real life, but what we have in real life are slight or small perturbations of integrable equations. Therefore, when we study applicable finite-dimensional systems, very often what we have to take one or another integrable system and to study property of these integrable systems under small perturbation. And the situation is very similar when we start to talk about nonlinear partial differential equations. One of the most spectacular discoveries of this theory of the mathematical physics from which is related to analysis in the second half of last century was the discovery of integrable partial differential equations. Maybe the most famous is the Korteweg-de Vries equation. But then the situation again is the same. So KdV equation never appears in mathematical physics and in physics in a pure form. Always to derive KdV equation as a tool to describe one or another physical phenomenon, we do the same job. Namely, we take exact physical equation, we consider it one or another regime, and we have throw away terms which we considered as small under this or that physical situation. Therefore, we arrive again at the same question: how properties of the remarkable solutions of KdV equation and for other equations, how they persist under perturbations. And this is what my talk is about. So equations will be rather simple and functional spaces will be very simple, but the point will be to understand what happens with solutions for these equations. Okay, so this is a KdV equation. I will consider it under periodic boundary condition, because the same equation on the whole line with finite L2 norm, it's absolutely another problem which asks for absolutely another tools. And I restrict myself to the case of solutions which have zero space average. Well, it is immediate that this equation can be written in the following form. We have to take functional, which is called Hamiltonian of the KdV equation. We have considered variational derivative of this functional, and then our equation has a form u dot plus d over dx of variational derivative. Since d over dx is a skew-symmetric linear operator, and since this is a gradient, then the KdV is a Hamiltonian partial differential equation. That is to say, if we consider KdV as an infinite dimensional system in one or another functional space, that what we will see is an infinite dimensional Hamiltonian system. Well, as I said, it is not that important for me in which functional space shall we consider the equation. So I will take the simplest one, which is sufficient for my purposes. This is a L2 functional space of functions with zero mean value. The norm in this space which will be denoted like this. So KdV defines a Hamiltonian dynamical system in this space. And as I said, this dynamical system is integrable. It's integrable among other things. It has infinitely many integrals of motion. It is not that easy to explain what does it mean that it is integrable, and it is not that easy to explain which integrals of motion should we pick up just to simplify analytical study of perturbations of equation. Maybe the best way to do this is the term of the nonlinear Fourier transform. Okay, nonlinear Fourier transform. Nonlinear Fourier transform is an analytical map which maps function u of x with zero mean value to a vector, infinite dimensional vector, which has infinitely many two-dimensional components v1, v2, v3. So every Vj is a two-dimensional. Vj is a two-dimensional component number j of the psi of u. This mapping has quite a number of really remarkable properties. Firstly, this is a global analytic symplectomorphism. So it means that this is analytical map. Inverse map is analytic, and it is symplectic if we provide the functional space of U of x with the usual symplectic form of the KdV equation, which corresponds to the skew operator d over dx, and if we provide the space of sequences, which what is called KdV symplectic form. This is the KdV symplectic form. Maybe just another small, just to make it another. I want to mention something else. So this is the map psi. If I take for the definition of the map psi Sobolev space Hs of the function with zero mean value, then the map psi maps it to the space H small s, which is the L2 weighted space, which corresponds to the Fourier coefficients to the Fourier coefficients from the functions from Hs. What is written next, that its differential at the origin is the precisely Fourier transform. So differential psi of the region, I will denote the map psi 0. This is simply Fourier transform, which is doing the following. I take for a function u of x, it corresponds to the line. It corresponds the line formed by the Fourier coefficient corresponding to a series in the to the sine cosine Fourier series. So up to now this is not that striking, but now I will tell about something which is really very striking property of the KdV equation. Denote by the ij 1/2 of the modulus of the vector qj squared, and denote by the qj corresponding angle. So you see what happens here. So the variable vj lives in a two-dimensional plane number j. So this is where the vector vj lives, and ij is radius squared divided by 2, and this is qj, and this is ij equals to 1/2 of the radius number j squared. Good. So then if we write the Hamiltonian of the KdV equation in the v variable, we will see that the Hamiltonian becomes an analytic function of actions only. One immediately checks that the variable I and q are symplectic coordinates, and therefore one just immediately sees that in the variables I and q, KdV equation has this remarkable integrable form. So since Hamiltonian doesn't depend on q, then the d over dt of ij remains 0, and then the equation for the motion of the variable qj is the following. Just note that since ij stays still, then for every solution this is a constant, right? Therefore we can solve this equation immediately. It means that this is equation which is written in the integrable form. If we instead write down KdV not in the variables I, q, but in the variables vj itself, in this variable, so we'll see that in the variables vj, KdV takes the following form. You see, so vj dot equals to minus phi j is a two-dimensional vector field, and this two-dimensional vector field is perpendicular to the vector vj. So this is the same story again. So vector vj rotates along a circle in such a way that the radius remains the same. So this is the same story again. This is integrable presentation of the KdV equation. Okay, people with experience with classical finite dimensional Hamiltonian system immediately recognize in this form of writing down the Hamiltonian equation Birkhoff normal form. So so ij are integrals of motions, the actions, and qj are the corresponding angles, and that is that the v variables provide global Birkhoff coordinates for the KdV equation. What is here really remarkable? That for finite dimensional Hamiltonian system of any practical importance apart from linear systems, we also can construct Birkhoff variable, which puts them in this elegant form above, but we can do it only locally. Normally we do it in the vicinity of equilibrium. For the KdV equation, for some God-given miracle, we can do it globally in the whole phase space, and we can do it in just analytical way. And it's a very long story. So the construction of the Fourier transform, it's a very long story. It took maybe just 15 years, and it was recently it was summarized in the book by Kepler-Purcell. But the object is so complicated that so for every practical purposes, for serious practical purposes, we have to improve it. So for the purposes of this research, the result of Kepler-Purcell were improved in my joint paper with Galina Perelman. Galina is from Petersburg, but she's not a relative of the Perelman. Just maybe what our result, what we proved there, just to show you, our result shows that the psi variables are even better than I said, because what we prove is the following. So this is a map psi, this is psi naught. Let us consider psi minus psi 0. So let us consider the non-linear part of the map psi. Then our result is that this is analytical map from the space Hs not to the space H small s, but to the space H small s plus 1, L plus 1. So it means that the non-linear Fourier transform is a quasi-linear transformation. Is a quasi-linear transformation which is absolutely importable, absolutely crucial for analytical studies of the equation. Okay, well, and let us provide you with a trigonometrical basis which corresponds to the Fourier series which I have spoken about. I will use it. I will use it very soon. You will see why I need it. Okay. Now I will move to my main task. So my main task is to discuss perturbations of KdV. I will discuss perturbations. I will speak only about perturbations of the KdV equation by lower order terms, because otherwise task becomes much too complicated, and small terms. So I add onto equation small right hand side, which is an analytical function of u, first derivative of u, and the second derivative of u, right? And also, since fortunately this suits perfectly well to the topic of this workshop, I will consider perturbations with randomness. Also, I consider the case where, apart from this perturbation, I will add a random force. Random force here is as usual, because I take random force right in time, because for the purposes again of this research, I have to make quite a lot of rather heavy analytical calculations, and Ito calculus helped me a lot to run them through in a rather compact form. So just the force is right in time, smooth in x. You see I have decomposed it in the basis ux, and all coefficients bj are non-zero. So I presume that there is a noise in every Fourier mode, and size of Fourier coefficients decays faster than any negative degree of j. Therefore, as a function of x, it is smooth. And bj's here are standard independent Wiener processes. I put here factor gamma for the following purposes. So mostly because usually gamma will be either 0 or 1. So if gamma is 0, the noise is switched off. If gamma is 1, the noise is there. But at the very end of my talk, I will briefly mention that there is another very big possible activity. Consider the case when gamma is positive but small but positive. Okay. So roughly situation like this. I would like to study this equation, but I cannot prove much. But I can prove quite a lot for this equation. So the message, one of messages is that if you study a really complicated phenomenon of nonlinear partial differential equations, randomness helps rather than randomness disturbs. It is easier to study SPDEs than to study nonlinear PDEs. Okay, task. Let us study solutions for the perturbed KdV equation, for the perturbed KdV equation with given initial data. This will be changed at the last slides on long time intervals.
Do you need the first term on the right hand side?
Do I need what?
Do you need f on the right hand side?
F?
Can you drop that term?
I think so. You will see. There will be sort of the humanitarian part, and for humanitarian part there will be anything. But then the question is what I can prove. If I think yes, I can. This is the right question. What you ask is the right question. You see, this would be an empty equation if I spoke about linear equation, but equation is non-linear. Therefore, even if I perturb linear equation by small trivial force, it is non-trivial task to study the object. And we will see very soon that this is right time scale. So you could ask me why not to study up to times of order epsilon to minus 2. I will say, wait, you will see. Okay, so now, since I mentioned nonlinear Fourier transforms, that of course let us apply nonlinear Fourier transform to this equation. And let us write the perturbed KdV equation in the v variables. This is a component number k of this equation. It has drift, it has diffusion. Gamma is here, and when I gave a preliminary version of the Stoch and Born, Felix absolutely rightly mentioned that now pk also depends on gamma because of eta term. So pk slightly depends on gamma, but I simply removed it from my notation. As it is well known that it is convenient in this group of questions. It is convenient to go to the slow time. Tau equals to epsilon times t. In the slow time tau, I simply multiply just right hand side by just epsilon to minus 1. But due to this eta calculus scaling, when I do this, I have factor exactly 1 in front of diffusion. So indeed it looks much better. It looks much better in the slow time. Now, in the slow time, my task is to start the solution for this equation for tau between 0 and 10, where t capital is any fixed constant. Well, in the v variables, I can alternatively use vector of actions and vector of angles. Therefore, I have two tasks: to study actions on long time intervals like this, and to study angles on long time intervals like this. For a number of reasons, so historical, physical, and technical, the main task is to study behavior of actions. Because you see angles, they simply rotate in some silly way, they rotate very fast. But just angles when epsilon were 0, actions stay still. But when we switch to the perturbation, actions start to change slowly. And the task is to understand, the main task is to understand how they change. Good. Okay, and starting with Laplace and Lagrange, which is already something like 210 years. Questions like this were considered, analogy of questions like this were considered for perturbations of classical integrable systems, and the first who were doing this systematically, they were Laplace and Lagrange. Laplace was doing this, essentially Laplace was doing this for the purposes of study, to study celestial mechanics and to give a lot of practical results concerning behavior of solar system. They were, by the way, important for the purposes of navigation in early 19th century. And Laplace managed to get something like 1/2 of the golden medal of Royal Society of London, which came with a really big amount of money, because he improved quite a lot quality of navigation because of quantitative study of the behavior of stars, which he achieved with his tools. Laplace mentioned it took for him, I don't know, it was the main task of his life. And he claims that using this technique he proved stability of solar system. Of course, this is not the case. It is open problem. This is still an open problem. What Laplace proved, that he proved that the averaged equation, effective equations, are stable. I will refer to this phenomenon a bit later on. So what they were doing? They were doing the following. Okay, look, I have equation written in the I variable, but I variable are equivalent to the actions and angles. Let us write equations for the actions, which follow from the equation for the v variable. Here is it. Equation for action I depends on the vector of actions, and of course depends on the vector of angles. And now in the right hand side, in the left hand side, I have no term of order epsilon to minus 1, because terms of order epsilon to minus 1, they are present only for equations for angles. So angles rotate as a hell, but actions they change slowly. And then this classical averaging procedure, which is at least due to Laplace Lagrange, as usual it should be later than this, is the following. Let us take what we have on the right-hand side, and let us average this equation in Q. And after this averaging, we will get a system and equation on the i's only. Now this is stochastic equation on I, you see, and every right-hand side depends on I only. Here averaging means the following. So averaged vector field, this is precisely averaging, and the averaged diffusion is the averaging due to the rule of stochastic analysis. I do not want to stop just now. I will touch this issue a bit later. Then Laplace Lagrange claim was that the solution of the average system will approximate the actions. Well, I guess that Laplace Lagrange never specified on which time intervals they approximate the actions, because for solar system it is not that easy, and then by the way, then epsilon 10 to minus 4 for the solar system. It may be not so impressive. So simply this is what they did. They just considered averaged equation. But they studied them. But this is a classical averaging, and the fact that this classical averaging was justified only in 20th century, essentially mostly in Soviet Union and in Japan. So mostly started with Nikolai Bogolyubov before the war, and after the war a crucial contribution was in Soviet Union due to Nishtat and Anosov, and in Japan due to Kasuga. So now this stuff is explained very well in a number of books. For example, in these two. Okay, we can try to do this for infinite dimensional system. We have achieved something, but we cannot achieve much. Why? Because if you speak about infinite dimensional systems, this averaged equation becomes a very bad equation. Why it is very bad? Because look, what is the phase space for this equation? This is a phase space of positive quantities. So now the phase space is an infinite dimensional positive octant. But infinite dimensional positive octant is a terrible phase space. It's a terrible phase space. It is not. It is unlinear. And when we are at the boundary of the octant, equations degenerate. For example, diffusion degenerates, and we have weak singularities at the boundaries of this octant. And of course, boundary of infinite dimensional octant is everywhere dense, right? So this is really a very, very messy equation. So my suggestion is just to proceed differently, similar but different. And this is the issue of effective equations. Okay. So just once again, what we are speaking about? We are speaking about the perturbed KdV equation, which is written in the v variables. And this is the vector notations. So here beta is an infinite dimensional version of infinitely many copies of Wiener processes. P of v is a vector field in a Hilbert space which is drift, and beta of v is an infinite matrix, dispersion matrix. Then I construct what I call effective equation for equation 2. Effective equation for equation 2 is the equation 3, which contains no small parameter now, where we have effective drift, and when we have effective dispersion operator. Effective dispersion operator. How these objects are defined? So how to define effective drift? Look. Let me remind you that the v variables, my v variables is a direct sum of infinitely many copies planes, of infinitely many copies two-dimensional planes, plane number 1, plane number 2, plane number j, and I have infinitely many of them. For any vector from the infinite dimensional torus, let us consider linear transformations in the space of v vectors, which rotate component of the vector component number j of the vector v by the angle theta j. You see this? So action radius stays still, but the angle is being linearly rotated by the vector theta. So this is a linear transformation of the space V. This is obviously unitary linear transformation. Okay. So now look what happens. I have a Hilbert space, which is a space of vectors V. on this Hilbert space, I have a vector field phi. But diffeomorphisms and also linear diffeomorphism acts in the space acts on vector fields. So the linear diffeomorphism p theta, its action on the vector field p is the following vector field. I have to evaluate p at the vector p theta of v. And now, since p theta is a linear transformation, I have to imply inverse transformation. This is how linear transformation p theta, how this unitary operator p theta acts on the vector field p. Okay. So you see, so this is the action. And now let us average this action against all possible rotations theta, where theta is taken from the infinite dimensional torus, and the infinite dimensional torus is provided with the most natural measure, which is Haar measure, but this is simply trivial measure d theta 1, d theta 2, d theta 3. So this is very natural. With averaging of effective dispersion, with construction of dispersion operator, situation is more complicated. You see, in the equation 2, I have a dispersion operator which is called B. Let us consider square of this operator, square like this, then just everybody here of course knows that this square is called diffusion operator, diffusion operator. Then let us average this diffusion operator under action of the linear transformations p theta. If we will think a bit in terms of differential geometry, what is the right formula for the action of linear transformation, then the answer is the following. So this is how linear transformation p theta acts on the self-enjoyed operator, acts on the self-enjoyed operator bt. And I consider this action, and I'm just average equation in all possible rotations theta. This is then the right hand side is nothing but average diffusion. And the effective dispersion operator is a non-symmetric square root of the average diffusion. Okay, so there is the real issue is the following. So traditionally in equations like this, traditionally or more often, people take for a square root symmetric square root. It would be good to do this here, but it doesn't work. Why? Because in the right hand side I have a bounded symmetric self-enjoyed operator in a Hilbert space. This operator is non-negative. Of course I can extract symmetric square root of this operator, but the spectrum of this operator touches zero, touches the origin. Therefore, the square root, usual symmetric square root, would have a singularity. Actually, as a function of v, the square root would be only Hölder one half smooth. If I have Hölder one half smooth component of my equation, I am in a very bad shape. So Luis in first talk explained us that how serious are difficulties having Hölder components in our equation, even if we're speaking about linear equation, but I'm speaking about non-linear equation, so I'm dead. Therefore, what is a small miracle here? What is here a small miracle? That this operator, which is non-negative self-enjoyed symmetric operator, it admits a non-self-enjoyed square root like this, which is a function of v, is analytic, and which is completely under control. Well, construction of this square root was I extracted from a paper by Pyatnitsky Pardu. So this is okay. So it has some story. People were using tricks like this. Okay. So by definition of the effective object, so this is the equation which I'm speaking about. By definition of this effective drift and the effective diffusion, this equation, this is a nice equation. It is invariant under the rotations p theta. That is to say that if v of tau is a solution, of this effective equation, then any rotation also is solution. Of course, it's a weak solution. Right? So. Questions.
When you are writing down this integral over with respect to the half measure,
Yes.
I mean, is it clear that, that there are no locking? I mean, what do you call this? No locking of the cues. I mean, no additional invariance, resonances. I mean,
No additional resonance. Well, I simply integrate. So in this.
I mean, if you have an additional, then the invariant measure is no longer the half measure on the torus, right? If you have
This is correct because I have no torus because I kill torus in a sense. Okay, so maybe so I do not understand your questions, but maybe I can say the following. When I do the following procedure, I obviously very strongly corrupt the angle component of solutions for my equation. So you see, when I pass from equation to the effective equation, I will explain it very soon, that I will keep control of actions, but I completely lose control for the behavior of angles. This is more or less what you were asking, no? Okay, so then maybe just wait till the break. So this is the construction anyhow. This is the construction. Then what I'm going to do with this construction? It's another question. Okay, averaging principle. Let V epsilon be a solution of the perturbed KdV equation written in the V variable, and let us V0 of tau be a solution of the effective equation 3. Then let us consider actions of the perturbed equation. Let us compare them with the angles with the actions of the solution for the effective equation with the same initial data. Then the latter will approximate the former on long time intervals. This is precisely the statement how people state averaging principle, with only difference that now the approximating objects comes as actions for solutions of an auxiliary equation. Therefore, I have two tasks: prove the averaging principle for various classes of perturbations of the KdV equation, and to study properties of the effective equation 3. So just to study properties of the, so to say, averaged equation. Well, both tasks are very popular in the finite dimensional analogy of this activity, because as I said, so what Laplace essentially was doing, he studied properties of the averaged equation. And the importance of task 1 is obvious, because so does it make a sense, or why does not? Let us consider some examples probably. No, just what I'm saying about it is related with one of the challenges in analysis of nonlinear partial differential equation, which is called Wisdom averaging. And the relation is the following. What I'm speaking about? I'm discussing perturbation of fast in time oscillating solutions of the KdV equation. What does it mean? I take roughly what I'm doing. I take this classical integrable solution of KdV equation. I go to the slow time. I write down this solution in the slow time. Then of course they start oscillate fast because it's slow time. I add some small perturbation to this equation. It became small. It lost factor epsilon because of passage to the slow time. And I study solution for this equation. And for example, I'm trying to understand if how can I use solutions of the KdV equation to construct curves which will approximate solution for this equation. This is what I'm speaking about. This is my task. Similar, one can consider perturbations of solutions for the KdV equation which oscillate fast both in space and time. What does it mean? I take unperturbed KdV equation, I take an integrable solution for the KdV equation, and I write this solution of the KdV equation using slow time and using slow space variable. Then, if I had a perturbation, then the perturbed equation start to look like this. Okay. So nothing happens. Simply I passed to slow time, slow space, and as a result, now unperturbed solutions for the KdV equation are fast oscillating functions both in space and in time. I add perturbation, or maybe I even consider the case of zero perturbation, and I take any initial data, which now is a function both of slow space and the usual fast space. And the problem which I'm addressing, which is absolutely very important problem, which is very well known for people from physics and for the mechanics of solids. So how to approximate solution for this equation with this initial data if you have in hand exact explicit formulas for the solution of the KdV equation. And the corresponding averaging principle is due to wisdom. It is now something like 40 years old. And it was not justified completely. It was never justified completely for any class of perturbations for KdV. Despite we have very important, very interesting, very useful works of Livermore and Venikides. Okay, so my perturbations are of course simpler because I consider the case when everything oscillates fast only in time but not in space. This is more complicated, but I can prove theorems. So my belief is that maybe progress in this problem also may be achieved if you pass to the stochastic partial differential equations. But this is again, so now I will forget about wisdom aberration and I'm going back to my problem. I have introduced this notion of effective equation. Let us consider two examples where I can well describe these effective equations. First case. Let us consider the case when the perturbation for the KdV is given by the following term. When the function epsilon f, which I add to the right hand side of my equation, is simply epsilon times Laplacian. This is perturbation which is intensively considered by physicists in books. For example, there is a famous book of Novikov, Zakharov, Pitaevsky, Matveyev, theory of solitons, and this equation can be considered there. And there are some formal recipes how to study solutions of perturbed equations like this. Okay, so now we have like this. Denote by the delta hat the Fourier image of Laplacian. So this is Laplacian written in terms of Fourier coefficients, as usual, right? As usual. Then now claim. So this is lemma. So lemma. Now the effective drift is a Fourier image of Laplacian. So this is a linear operator which is Laplacian written in terms of Fourier coefficient plus a lower order term. So this is operator for the 2, and this is operator of order at most 1. And to get here this gap, which is crucial for my analysis, this is why I need this smoothing property with the linear property of the nonlinear Fourier transform. So now the effective equation 3 is a quasi-linear stochastic heat equation. So this is operator for the 1, and this is analytical. There are no derivatives here. It is very friendly, so it is very well understood class of stochastic partial differential equation. Second example is the following. Consider non-stochastic Hamiltonian perturbation, which is a Hamiltonian perturbation. So let us put in the right hand side of KdV equation some small Hamiltonian perturbation with epsilon in front of. And now let us gamma equals to 0. So now let us assume that we have no stochastics. Then in this case, the effective drift is an integrable Hamiltonian vector field. So this is a vector field where the action stays still and the angle rotates fast. So now the effective equation is again integrable Hamiltonian partial differential equations where the action stays still. So in this case, averaging principle, if it is true, would imply adiabatic invariance of the KdV actions for the solutions of the perturbed KdV under small Hamiltonian perturbation. So I cannot prove this. This is simply to show that the averaging principle, which I announced, it is reasonably related with some other options. But just I can prove this. Okay, so let us go forward. Now I will pass to the series. I have two results below. They are presented in two publications. First is my joint paper with Andrei Pyatnitsky. It is now 2 years old in the Journal de Mathématiques Pure Appliquée. And the second paper is from this year, and it can be found in archive. And just philosophically and just ideologically, my talk is more or less in the spirit of this work. Okay, so now theorems. Now consider the original randomly perturbed and damped KdV equation. In the case when the perturbation is the Laplacian plus noise. Is Laplacian plus noise. Let us consider the case. When we have Cauchy initial data. So we know our solution at time equal to 0. Due to the example 1, which was on the previous slide, now effective equation is the following. Now effective equation is a quasi-linear heat equation like this. Here f prime is an analytic operator for the 1. This is linear operator for the 2, and the matrix depends on v, but not on gradient of v. So as a function of v, it's a matrix valued operator for the 0. Okay. This is a quasi-linear stochastic heat equation. It's another lemma that this equation is well posed. For every smooth initial data, this equation has a unique smooth solution. It is not okay. So well, Sobolev scale does not suit so perfectly well to this equation. For example, I cannot tell that for HS smooth initial data, this equation has just a HS solution, but I know that for smooth it has smooth solutions. Theorem. Let U epsilon of tau be a solution of the perturbed KdV equation, and let V of tau be a solution of the effective equation. Let V epsilon of tau be a nonlinear Fourier transform applied to this solution. And then let us evaluate actions of the solution, and let us evaluate actions of the solution for the effective equation. Then when epsilon goes to 0, actions of the solutions for the exact equation converges to the actions of the solutions of the effective equation in distribution. In distribution. So this is precisely averaging theorem for actions. Averaging theorem for actions. Now, what happens to angles of our solution? It turns out that under the limit epsilon to 0, the phases, the angles become uniformly distributed on the infinite dimensional torus, provided that I will modify them in time. So precisely it means the following. Let us consider solution the epsilon of the perturbed equation written in the v variables. Let us consider angles of this solution. Let us consider law of the angles of this solution. Let us consider how these angles are distributed on the infinite dimensional torus. This is the measure on infinite dimensional torus. This measure depends on the parameter tau, which is time. Let us modify it with any function of tau. Modify it, and it should be only continuous function. Then this modified measure converges to the Haar measure on the infinite dimensional torus when epsilon goes to 0. Okay. Therefore, effective equations, they take the job of taking a control for the behavior of actions of my solution when the size of perturbation goes to 0. Effective equation give me no information. They have nothing to do with the behavior of the angles of my solution when epsilon is small. But the behavior of angle solutions is simple because when an epsilon goes to 0, then the angles becomes uniformly distributed on the torus. This is known as a stochastization of angles in modern physics, and this is a postulate for all most of studies of the weak turbulence, and this kind of convergence can be found many times in papers of the Haar, but there it is written that we believe that this is true. Here, since everything is rigorous and I have a white noise on the right hand side, this is a theorem. Good. So now, but effective equations can do more. Just the double limit, dump-driven KdV, and this is a work in progress. So just I hope to finish this year jointly with Romain Cherikan. There are some okay. The existing techniques allow to prove that the effective equation 5 has a unique stationary measure pi. You see, so this is a measure with non-additive noise, but I have two huge advantages. First, I know that this noise is not degenerate. It's a lemma again. and I study this equation only in class of solutions with fast decaying tails. So all moments of all Sobolev norms for my solutions are finite. Therefore, real claim is that this equation has a unique stationary measure such that all moments of all Sobolev norms are finite with respect to this measure. Okay. Then consider the original randomly perturbed KdV. This equation definitely has a unique stationary measure. Let us denote this stationary measure P, and let us denote this stationary measure mu. Then this is, so to say, this is why unique stationary measure is important, that in distribution, when time goes to infinity, every solution for equation 6 converges to this unique stationary measure mu epsilon. Let us analyze action components of this unique stationary measure mu epsilon and compare them with the actions of the unique stationary measure mu. Then just of course, then just let us do the following. Let us take this unique stationary measure mu. Let us pass from the variable u. Let us pass from the variable u first to the variables v, and then to the action angle variables I phi. And let us pass this unique stationary measure. Let us pass this unique stationary measure mu epsilon. Let us write it in the variables I phi. That what happens, that when epsilon goes to 0, this unique stationary measure mu epsilon converges to a unique limit. And this unique limit has the following form. This unique limit is a direct product of two measures. One measure sits in actions, another sits in angles, and another sits in angles. The measure sits in angles, of course, it is hard measures before. As the measure which sits in actions, which gives us limiting distribution of the actions. Of course, this is nothing but the I component of the measure pi. This is almost the end. Yes, accordingly we have the double limit. For any smooth initial data u0 of x, let u epsilon be a solution of the down-driven KdV equation 6 with the given initial data. Then the double limit which I have here exists. First time to infinity, second perturbation to 0. And this double limit as a product measure, where the second component is the Haar measure, and the first component is the distribution of actions for the stationary measure, for the unique stationary measure for the effective equations. Then now this is claimed. So when gamma, which is intensity of the force, goes to 0, the unique stationary measure for the effective equation can be effectively decomposed in asymptotical series in gamma. Therefore, I have a bunch of asymptotical results, at least in principle, which are not written yet. But these objects may be effectively decomposed in asymptotical series in small parameter, and I'm sure that it has a physical meaning, but this has to be checked yet. Now summary. Consider the randomly perturbed and damped KdV equation. Voila, here is it. Then for epsilon small, its solution may be well approximated in terms of the solution of effective equation in the following sense. When time t is comparable to epsilon to -1 or is smaller than this, then the distribution of the solution of this equation simply converges to the distribution of solutions of effective equation, as I said. But when times becomes very big compared to epsilon to -1, then the distribution for the solution of this equation can be effectively described in terms of unique stationary measure for this equation, in terms of Haar measure in torus. So you see, so this equation gives us extremely effective control to the long time behavior of the solution for this equation. Actually, as I said, when I said that about stationary solutions, I said that I'm sure that this is true. No doubt, it's a matter of time. It's a bit slow because also Armen now, unfortunately for me, is the head of department, so It is not as fast as I would like. But what there is another phenomenon which is conjecture, which I strongly believe is true. Look what I believe what happens here. I take a solution for equation u epsilon tau. Let us speak only about actions for this solution. Let us take effective equation u0. Let us take effective. I used fast time, slow time tau. u0 of tau, and again distribution. Then I really believe, and I really have really good reasons to believe, that this measure converges to this measure, and epsilon goes to 0 uniformly in time. This is pure stochastic phenomenon, which really tells us that effective equation is really good tool to control behavior of solutions of the perturbed equation. But of course, I am very strongly based on the fact that the unperturbed equation is integrable. So therefore, I started with quoting Poincaré. So it's a good thing to study. Okay, just thank you for the attention. That's all.
Maybe very trivial question, and maybe you already answered this question. Is so, which other operator instead of uxxx in this equation you can consider by similar method? Do you know something, or do you have some ideas?
This is it's yes. Well, just of course I have no doubt that if you take degree of Laplacian bigger than 1, of course it will be the same and only better. If you have degree of Laplacian of degree smaller than 1, I'm just less sure. So something should be checked. Of course, this kind of result is about nonlinear partial differential. Of course, perturbation cannot be arbitrary. Certainly it is not. So just for any, I think that I'm very far than just okay. Of course, it works for some other perturbation, but just I cannot specify for which ones.
So, I mean, is this kind of, I mean, coming back a little bit to this
Yes.
question of the resonances, and
Yes.
so you say here, when the epsilon, when you have this scaling of the two terms, and you have a white noise,
Yes.
then you actually can show that the Q will be the Haar measure will converge to the Haar measure on T.
Yes, I do, right.
But I mean, is this crucial? I mean, could it be that when I scale the stochastic noise slower, so that it will be disappearing in the limit, this property?
Of course, that's absolutely right question. It's absolutely right question. So just for example, here it's absolutely right question. For example, I would state, for example, the basic, so to say, the basic form of this question is the following: can I prove something like this without noise at all? Or with noise weaker than I use here. Just let me give you just very small comments. Why need noise here? Why need noise? Because from what I said, it follows from what I said about KdV equation. It follows the following. KdV equation, the phase space is related to the invariant torus of finite or infinite dimension. Along every torus, I have a linear motion. This linear motion is described by frequency vector W. So motion is q dot equals to W. So typical torus is very good, and there are no integer relations between components of the W vector. And then I can, in the tiny vicinity of this torus, I can average everything perfectly. But there are bad tori which are resonant. And the main task of proving theorems like this is to understand what happens in the vicinity of resonance tori. This is really very difficult. So now, in finite dimensional versions of questions like this, technically very strong people like Dolgopyat are writing pages of something like 100 pages to understand what happens for rather simple equations where this difficulty is present. So instead of to understanding how to fight with resonances, I simply added noise. And noise pushed me away from tori where there are resonances, so I simply cannot neglect considering of the resonant tori. Therefore, of course, the equation is absolutely right. So I use rather intensive noise to push me out of resonance story. If I use weaken noise, will it be sufficient? Well, this I did not check. Of course, if to make technique sharper, then but okay, I'm pretty sure that it can be reduced. But up to which level, I do not know. I don't know.
I had one. So you're comparing the original model and the the limit model always on the level of distributions, not pathwise.
Right. Because I cannot rule out that I believe, and I'm okay. Hard to say that I'm sure, but I strongly believe that it also I really believe that if you remove noise from here, but if you take random initial data, that the result will be the same. But it will be much more complicated. So I do not think that it's really about measures. So this is really good equation. So what I'm saying. So this is really good equation to study small perturbations of KdV. You see, it's another point of view on the averaging of integrable systems. In finite dimension, people were not concerned with this because if you have octant of dimension 3, bounding of octant is of no importance for you. But an infinite dimension becomes crucial. So I think that this is right substitution for the averaging ideology. Therefore, I think this is important for many other classes of perturbations, also without randomness.
Here again.